This is the brief on orthogonal flow dynamics. So we're looking at a study called Orthogonal Flow Dynamics and Energy Conservation. And what it shows is something pretty cool. How the actual walls of a container dictate what the fluid inside is even allowed to do. Okay, first up is something called the Helmholtz decomposition. Now it basically just splits fluid motion into two. Let's call them teams. You've got flows that swirl, right? Like water going down a drain. Then you have flows that expand straight out, like air from a balloon. The question is, do these totally different movements mess with each other? Second, this all comes down to the boundary condition. It's really just the rule at the edge. For the math to work, the fluid has to, well, glide along the walls instead of just punching right through them. And when the fluid behaves, stays in its lane, those two flow types become orthogonal. That's just a fancy way of saying they completely ignore each other. And finally, this is where it all clicks with energy conservation. See, when that boundary rule is followed, the energies from our two teams don't mix. You just calculate the swirling energy, calculate the expanding energy, and add them up. Simple. But if there's a leak at the edge, you get this interaction energy, which proves it's the container's limits running the show. In short, energy conservation isn't some property of the liquid itself. It's all about whether the container's boundaries keep everything in its own lane or let it all mix together. In physics, the edge defines the middle.